The most distant human-made object in the universe is sending usable information to Earth again.
It's of a long journey, but now the Voyager 2 spacecraft has finally bid farewell to our solar system.
In the cold emptiness beyond our solar system, where sunlight fades into memory, an aging human-made probe has continued its silent watch. Voyager 2, drifting for nearly half a century, was never meant to return, yet it has just sent back a signal no one was prepared for.
NASA couldn't regain control of the lost Voyager 2 probe after a heartbeat signal was picked up.
What first sounded like harmless static carried a precise and unnatural rhythm. When experts traced it, they discovered something unsettling following Voyager 2, something that should not be there, turning the old probe into a stark reminder of a truth we may not be ready to face. Origins of a space legend. The voice of the cosmos that we now trace back to an instrument voyaging far beyond our familiar skies began with Voyager 2.
After it was launched, NASA is this morning searching for its Voyager 2 spacecraft.
A probe launched by NASA in the late 1970s. Its mission? To journey past the inner realm of our solar system and explore the outer giants, and then continue onward into regions never before touched by human-made machines. Voyager 2 was launched on August 20th, 1977 from Cape Canaveral in Florida, aboard a Titan Centaur rocket. At that time, it was already clear the outer planets offered tremendous scientific promise. Jupiter and Saturn, then Uranus and Neptune, each held secrets hidden in their swirling atmospheres, their many moons, their rings. Scientists envisioned a probe that might ride a rare alignment of these planets and use their gravity to swing around and reach distant corners of the solar system. Why did NASA build Voyager 2? Part of the answer rests in opportunity. Planetary alignments that occur only once every many decades made possible a grand tour of the outer planets via gravity assists. That tour promised to deliver flybys of Jupiter, Saturn, Uranus, and Neptune. The mission planners seized the chance to send not one but two probes, Voyager 1 and Voyager 2, each on its path. Voyager 2's trajectory was designed to visit them all, the giant gas and ice planets, leaving a legacy of exploration unmatched. Voyager 2's goals included taking photographs, measuring magnetic fields, detecting particles and charged gases, retrieving ultraviolet and infrared data, and acquiring the first close-up views of distant worlds. Aboard the craft were instruments such as an imaging science system, an ultraviolet spectrometer, a triaxial flux gate magnetometer, a plasma spectrometer, and more. Over time, its mission shifted from planet hopping to leaving the protective bubble of our sun and entering the vast interstellar ocean beyond. It is worth noting that Voyager 2 still carries a symbolic payload, the famous Golden Record.
Wonderful things they did exploring the outer planets of the solar system, except Pluto and all that. But the main attention goes to the Golden Record.
A gold-plated disc containing images, sounds, greetings in many languages, music from Earth, and the message of humanity in the cosmic night.
Any kind of effort to contact extraterrestrial life is more fascinating than knowing the chemical makeup of a mineral on Mars or something.
The craft is remarkable for many reasons. It is the only spacecraft to have visited Uranus and Neptune up close. It is still sending data across unimaginable distances. It has ventured into interstellar space, that domain beyond the sun's sphere of influence. The genesis of Voyager 2 reflects the bold spirit of its era, to send out a probe that could ride planetary gravity wells, explore worlds unseen, then continue on into the unknown. It was built to last far beyond its design lifetime, to face the extreme cold, the minimal sunlight, the emptiness beyond Pluto, and still transmit its whispers back to Earth. The team of engineers, scientists, and mission planners knew the risks. Instruments fail, power fades, communication delays grow. And yet they launched it with confidence that our species could reach outward, even if slowly, one light minute at a time, then one light hour, then beyond. Thus, this spacecraft began its journey, not just as an extension of Earth's mechanical curiosity, but as a sentinel of human ambition, carrying both scientific instruments and the very idea that we can reach out, gather knowledge, and listen. The origins of this space legend rest in the convergence of planetary chance, engineering daring, and the human yearning to understand the universe beyond the backyard of our home planet. Voyager 2's story is not simply about visiting planets. It is about venturing to the threshold of the unknown, and the mission's design recognized that the outer solar system held more than just delight for planetary scientists.
Of Earth, or our solar system, in terms of its direction from different pulsars.
It held the chance to learn how our sun influences far distances, how the bubble of solar wind ends, how the realm between stars behaves. And for that, we built Voyager 2. That foundation, its launch, its instruments, its planetary tour ambition sets up the stage for what comes next. How this probe traversed that journey, what it discovered, and now the strange message it has sent. Journey to the edge of the solar system. Voyager 2 carried instruments to image worlds, measure magnetic fields, sample charged particles, and transmit its findings back across the vast emptiness of space. From the very start, mission planners had in mind a rare planetary alignment which could allow the probe to swing by multiple giant planets using gravitational assistance. Scientists recognized that by harnessing the tug of large bodies, the craft could conserve fuel, increase speed, and redirect its path outward more efficiently. The trajectory was chosen so that the craft would take a longer time to reach Jupiter and Saturn than its twin, but this slower path granted the opportunity to continue on beyond them toward Uranus and Neptune. In this way, Voyager 2 became the only spacecraft to date to visit both of those ice giant worlds. The first major planetary encounter occurred at Jupiter. Here, the probe delivered sweeping views of the giant planet.
It's mostly empty space, so Voyager is likely to continue throughout our galaxy for potentially millions or maybe even billions of years without a collision.
Its swirling bands of clouds, its storm systems, its collection of moons. Instruments captured ultraviolet, infrared, plasma, and magnetometer data which revealed phenomena unseen before. After Jupiter, Voyager 2 pressed on toward Saturn. At Saturn, the craft revealed surprising details of the rings, shepherd moons, and inner satellites. It observed the tenuous spokes in the rings, found evidence of subtle structures and dynamics in Saturn's outer portions. By traversing these worlds, the probe did more than take spectacular photographs. It provided crucial data on how giant planets form and evolve, how their magnetospheres and ring systems behave, and how they shape their environs. With each flyby, the mission extended both its horizons and ours. After Saturn, the journey continued onward into more remote territory. Voyager 2 reached Uranus, becoming the first craft to do so. At Uranus, it discovered new moons, new rings, and offered first-ever close-up observations of the planet's tilted axis, its unusual magnetic field, and its frigid atmosphere. Then it traveled still farther to Neptune. At Neptune, the probe found the Great Dark Spot, fierce winds, dynamic weather systems, and moons revealed in sharp relief for the first time. The visits to Uranus and Neptune transformed our understanding of the outer solar system. Before the mission, these ice giants were little more than blurry points of light. After the flybys, they emerged as worlds of character and complexity. Voyager 2 fulfilled its so-called primary mission, but that was only half the story.
We were on a path we hoped to get to reach interstellar space while we still had power on the spacecraft to transmit the data back.
Once the planetary encounters were complete, Voyager 2 continued outward. The Sun bathes a vast volume of space with its solar wind and magnetic field, creating a bubble-like region around the solar system called the heliosphere. Beyond lies the heliopause, the outer boundary of the Sun's influence, and then the interstellar medium. By traveling outward, Voyager 2 became a messenger from that frontier. According to mission archives, it crossed the termination shock, the zone where the solar wind slows dramatically, and later passed the heliopause to enter interstellar space. At each step, the probe measured particle densities, magnetic field strengths, plasma waves, and cosmic ray intensities in a way that no earlier mission had done.
In fact, when we look at this dynamic activity in these extraordinarily cold regions, we really are at a loss to understand.
These measurements matter because they reveal how our Sun interacts with the galaxy, how the bubble around our system behaves, and how interstellar space differs from the world we know. Researchers used data from Voyager 2 to infer the sound speed and pressure in the heliosheath just inside the heliopause, insights only possible because the craft ventured so far. To travel this vast distance posed extraordinary technical demands. The spacecraft operates on a limited power source using radioisotope thermoelectric generators. As the years passed, the power has shrunk, so engineers have gradually powered down non-essential systems to preserve vital functions.
We have a 20-watt transmitter on the spacecraft, transmitting over 11 billion miles away.
Communication takes longer as the distance grows and the signal weakens. Commands take hours to travel, and responses come much later. Incidentally, design decisions made decades ago still hold. The orientation of the high-gain antenna must remain locked toward Earth. Attitude control must keep instruments pointed correctly, and the craft must weather cosmic rays and the fading glow of the sun. The next phase of this story brings us to an unexpected twist, a mysterious transmission from afar, something that prompts questions of wake protocols, low-frequency spikes, and what a probe can tell us when it is far beyond the planetary stage.
Only spacecraft that's gone by Neptune. Everything we know about those planets we know from Voyager.
The mysterious transmission. Although its primary planetary mission ended long ago, the spacecraft remains active in its extended mission. It is located far beyond the bulk of the solar wind's strong influence in a region where our sun's magnetic field and particle streams fade and the interstellar medium begins. Despite the vast distance, signals from Voyager 2 still reach Earth via the Deep Space Network.
By finding the probe's carrier signal, NASA was able to confirm that Voyager 2 is still broadcasting.
These transmissions carry faint but meaningful traces of how the cosmic frontier behaves. It is within these transmissions that researchers have picked up a curious pattern. Rather than strictly routine data about particle flux, magnetic field strength, or plasma waves, there are episodes that invite deeper attention. Episodes that hint at subtle, unusual behavior, low-frequency phenomena, and rhythms that repeat almost like a heartbeat in the darkness. One of the most intriguing aspects of the recent data involves a repeated spike at low frequency that appears at a fairly constant interval. According to reports that have circulated, this spike appears roughly every 11 seconds in the plasma wave measurements coming from Voyager 2. The signal is not loud in the conventional sense. It is not a loud burst or a glaring anomaly, but it is persistent and rhythmic, and that persistence gives it weight. When a low-frequency spike recurs in such a remote environment, it raises questions. What could cause an instrument designed for decades of quiet endurance to register a rhythm like that?
Both spacecraft were still operating when they reached interstellar space. It's really quite remarkable.
Could it be a natural interaction in the interstellar medium, such as a wave bouncing off a boundary or a shock front? Could it be an internal wake protocol event in the probe's systems themselves, or something entirely unexpected? The term wake protocol in this context refers to a mode where a spacecraft transitions from full active operations into a more dormant state, conserving power and waiting for commands while still maintaining contact and minimal operations to preserve its vital systems. As Voyager 2's power source diminishes, mission controllers have had to carefully manage which instruments remain active, which are turned off, and how to maintain communication over enormous distances.
That maneuver actually happened on the Voyager 1 spacecraft more than 16 hours ago, but the data is finally making it back to the Earth.
A rhythmic spike could be a feature of such a protocol, an instrument or subsystem waking briefly, transmitting a signal, then returning to standby. It might appear to originate from the probe's own systems rather than an external source. If the spike does correspond to a wake or heartbeat signal from the probe, then the repeating interval is less mysterious. What becomes significant is that we are able to observe such a heartbeat from a spacecraft nearly d-solar system wide away. But if the spike originates externally, something in the interstellar medium influencing the probe's sensors, then the implications become much richer. Voyager 2 crossed the heliopause, the boundary where the solar wind gives way to interstellar space, and has spent time in the heliosheath, the region between the termination shock and that boundary. In that region, magnetic turbulence, plasma wave phenomena, shock pulses, and other complex physics play out. Studies show that Voyager 2 has measured turbulence in the heliosheath and local interstellar medium spanning extremely low frequencies, on the order of 10.8 to 10.2 Hz, and translating to structures of immense size. The repeating spike could tie into one of these large-scale structures.
A lot of these particles stick together and grow into larger and larger particles.
For example, the passage of a global merged interaction region, a blast of solar origin charged particles sweeping outward, could interact with the heliospheric boundary and generate waves or pulses visible to the probe's plasma wave subsystem. It is conceivable that such a boundary interaction might produce a periodic wake or reverberation in the medium, something that the probe picks up as a rhythmic signal. Within the data that Voyager 2 sends, researchers have seen changes in cosmic ray intensity, plasma densities, and magnetic field orientation as it passed through the very local interstellar medium. These changes might correlate with waves or spikes, even if not precisely at 11-second intervals. Whether the transmitted spike is internal or external, the significance lies in what it tells us about either the probe or its surroundings.
This is the biggest, strangest mystery in all the universe at the present time. Wow. These are called fast radio bursts.
If from the probe systems, it may reflect the spacecraft's condition, perhaps a scheduled wake-up of a subsystem, a telemetry burst, a calibration pulse, or even the health check of a sensor. Understanding it will help engineers monitor the aging spacecraft, anticipate issues, and manage what remains of its capabilities. On the other hand, if the signal originates externally, then it may be telling us about the structure and behavior of the interstellar medium just beyond the Sun's reach. That region is still mysterious. We know the boundary between our Sun's domain and the galaxy is active. Waves, shocks, particle flows, magnetic reconnection all occur. A consistent rhythmic spike could mark a repeating phenomenon in that space, possibly the probe intersecting a periodic wake left by the solar system's motion through the galaxy, or a wave reflecting off the heliopause. If the spike is truly external and tied to an interstellar wave, then what we are hearing is the cosmos speaking in a rhythm we had not expected. Voyager 2 may not be sending an intentional message, but through its instruments it may be broadcasting an echo of cosmic structure.
Man-made object to reach interstellar space, the cold, dark region between stars, far from the influence of our sun.
The concept is profound. A spacecraft built in an earlier era still alive, still receiving signals from its environment, and still telling us about our place in the galaxy. The terrifying aspect comes from the scale of what we do not know. The boundary of the Sun's influence is not static. It is buffeted by solar storms, galactic magnetic fields, the flow of the interstellar medium. The conditions that Voyager 2 now traverses are more extreme than anything our planet or near-space probes experience.
Voyager 2 is 9 billion miles out. They're very near the edge of the bubble the Sun creates around itself called the heliosphere.
If Voyager 2's sensor is picking up a repeating wake, we are glimpsing something massive, slow-moving, and beyond our everyday senses. That sense of the unknown, of what lies beyond, is what gives this transmission its eerie and compelling quality. In the silence of interstellar space, every signal counts. The spike that recurs every 11 seconds is small but persistent. It calls for deep listening, careful filtering, correlation with multiple instruments, and open mind to the unknown. The message may not be about aliens or deliberate signaling, but it might be a marker of boundaries, of transitions, of the grand interface between our Sun's domain and the stars beyond. Voyager 2's mysterious transmission invites us not just to marvel, but to engage, to ask what lies beyond our solar bubble, to maintain and interpret the faint whispers of machines we sent out long ago, to treat that data as more than old telemetry, but as new windows. The probe continues to speak, and what it speaks may change how we conceive of our place in space, what it means for us, and what comes next. The messages still arriving from Voyager 2 reach us across a gulf of space so wide that the mind strains to grasp it. Every faint whisper that returns from the craft carries a reminder of how far human curiosity has traveled.
It actually happened last year, but NASA only confirmed the data on Thursday.
The probe's presence in interstellar space is more than a scientific achievement. It is a symbol of endurance and a measure of what patient exploration can become when a mission is built for the long road. At the time Voyager 2 was created, no one could predict with certainty how long it would last or what conditions it would face outside the protective environment of the solar wind. Yet the spacecraft continues to speak from a region where the Sun's strength fades and a new environment begins. That persistence reshapes our expectations of engineering and invites us to consider what future missions might accomplish if planned with the same patience and care. The mysterious rhythmic spike reported in certain readings also encourages reflection. Whether the rhythm originates from the probe's own systems or from something present in the space around it, The very fact that such detail can be detected across an unimaginable distance says much about the sensitivity and durability of the instruments. The signal itself, modest as it is, motivates researchers to think carefully about the physics at play in that far region. If it is internal, it teaches us about how spacecraft behave as they age in extreme conditions. If it is external, it reminds us that the universe is filled with subtle structures that reveal themselves only when we listen with enough patience. The success of Voyager 2 also suggests that humanity benefits from taking the long view. When the spacecraft was built, engineers had to prepare for challenges they could not entirely model. They created instruments capable of functioning well beyond their tested limits. The lesson for future deep space missions is clear. Patience and durability must guide design. Missions must be prepared not only for their first tasks, but for the unknown environments they may one day enter. As new missions are planned to explore the heliopause and interstellar regions, the data from Voyager 2 will become a foundation.
We were on a path we hoped to get to reach interstellar space while we still had power on the spacecraft to transmit the data back.
Future probes might carry more sensitive plasma sensors, more robust magnetometers, and more efficient communication technologies. The experience gained from operating Voyager 2 across so many years provides guidance for maintaining contact with spacecraft that exceed expected lifetimes. Engineers now understand more about power decay in nuclear batteries, instrument aging, and long-distance signal loss thanks to the long service of this craft. Voyager 2 invites us to reflect on our place in the universe. For centuries, humanity has looked to the night sky with curiosity. Yet the sky remained a realm of speculation until the age of spacecraft began.
It's the only spacecraft that's gone by Uranus. It's the only spacecraft that's gone by Neptune. Everything we know about those planets, we know from Voyager.
Now, thanks to machines like Voyager 2, we do not merely look outward. We listen to what space has to say. The transmissions coming from beyond the heliosphere tell us that the universe is not silent.
They're very near the edge of the bubble the sun creates around itself, called the heliosphere. We're getting very close to the boundary.
It is filled with subtle movements that occur on scales we cannot sense directly. The interstellar medium flows past the sun as our system moves through the galaxy. Shockwaves and plasma waves ripple across this boundary.
The sun creates this huge bubble of plasma, ionized material, goes outward at 1,000,000 miles per hour and creates a bubble.
Magnetic fields twist and fold in ways that challenge our models. Voyager 2 is listening to these movements and sending their signatures back to Earth. These details grant us a sense of belonging to a larger galactic environment. Our solar system is not an isolated island, but a member of a much larger sea filled with currents and tides.
So the solar wind carves out a bubble-like atmosphere that shields our solar system from the majority of galactic cosmic rays.
Understanding these conditions matters not only for scientific curiosity, but for any future dream of traveling beyond the sun's domain. Voyager 2 carries a golden record on which Earth's cultures, sounds, and greetings are preserved. This record was not intended as a literal message to another civilization. It was created as a gesture, a quiet statement of who we are in case the craft survives long after our time. The continued health of the spacecraft gives this gesture greater weight. The probe may outlive every person alive today. Long after its instruments grow silent, it will drift among the stars carrying that record. This knowledge shapes our sense of legacy. Voyager 2 is a statement that humanity's creations can wander farther than their makers and outlast their era. The spacecraft's survival encourages us to think not only about what we achieve in the present, but about what we send forward and who may encounter it someday. Eventually, the probe's power source will grow too weak to operate any instruments. Bit by bit, systems will fall silent until the craft becomes a dark traveler drifting with no active voice. Yet its silence will not diminish its contribution. It will have shown us how the solar system interacts with the galaxy. It will have taught us about long-duration exploration. It will have reshaped our understanding of what is possible. Future missions such as interstellar precursor probes may follow paths shaped by the lessons of Voyager 2. These missions might be faster and more advanced, yet they will owe their existence to the daring experiment that began in the late 1970s. As long as Voyager 2 continues to speak, the world will continue to listen. The faint rhythmic spike, the shifts in plasma densities, the subtle changes in the magnetic environment all remind us that the universe is not a static canvas. It is alive with motion, shaped by forces large and small.